That was good. Suppose f is continuous on AB, and f has a local extremum. Let's just, for the sake of definiteness, say maximum at C, which is inside. It's not one of the points AB, it's somewhere inside. Okay? F is differentiable on the open. So continuous on the closed, differentiable on the open. We know in advance it has a local max at some point. You can change all the words maximum in and the argument goes through the same. Then, what do you suppose? F prime of C is equal to 0. Okay, how would we show that? Well, at the local max, the derivative exists, right? So, can we write, now let's see, here's the point C. Let's pick a point below and a point above. We can always ensure that these points are inside A and B by picking delta small enough. So let's pick an interval, say C plus delta and C minus delta. And we get these points inside T1 and T2. The derivative exists everywhere, but in particular it exists in C. C is a local max. So f of T1 is less than f of C, right? And f of T2 is less than f of C. So form the difference quotient in C using T1. The limit as T1 approaches C of f of T1 minus f of C over T1 minus C. That's the difference quotient coming from the left. The difference quotient coming from the right is that. T1 minus C is a negative number. T2 minus C is a positive. F of C is bigger than either one of these, right? So this baby is negative, and this one is also negative. So the derivative then at C is equal to this. So this is apparently greater than or equal to 0. The other estimate is that minus over plus is less than or equal to 0. Second one where? Greater than or less than? This one. Here. Yeah. No, f of C is the local max.
So it's greater than negative.
Okay. F of C is the local max. So when you go to either side, it drops. The thing is, T2 is above C, and T1 is, yeah. The thing looks like this. There's C, there's T1, there's T2. So if I use the Newton quotient from the left, I get something greater than or equal to 0. The Newton quotient from the right, less than or equal to 0.
They have
take these. They have to, since it's differentiable, see these two things have to be equal. The only way that can happen is if that comes. So that's an important theorem. You don't have to prove Rolle's theorem if you prove this. I don't know what they call this. A max and local min zero. Critical value, it's a critical value thing. Yeah. If a function, let's see, you have a real function, and it's defined on a closed interval. Three things can happen. The local max and the local min can occur in three different places. Either they occur at the endpoints of the domain of definition, or they occur when the derivative is zero, or they occur when the derivative is not defined. Because if the derivative is defined, you're in this mode here, right? If the derivative is defined on the open interval, then if you have a local max and min, it has to happen at a place where the derivative is zero. The only cases outside that are the lateral derivatives, at A and B. That could happen. You have to check those as well. You might have a max or min at A or B. It's bigger or smaller than this one. And then if there's a place where the thing isn't differentiable, like the absolute value function certainly has a minimum of zero because it's not differentiable. But you won't pick that up by looking for f prime of x equals 0, right? And it's not the endpoint of the domain of definition. It's just a place where the derivative doesn't exist. That's the only three things that can happen.
I think the formulas that we normally have are critical values exist where f prime of x is 0 to 1.
Yeah, that's what
people forget about the 4.
Yeah. And I've been even telling them in calculus to check the endpoints of the domain of definition because very often the real axis is the domain of the function. So it's not operating. So you don't even bother going.
Well, we talk about the little perhaps those not check the endpoints as well.
Yeah. Oh yeah, you got to do that. Okay. See you Thursday.